Hey everybody, Dave Limburg in Hong Kong with yet another episode of the THD Podcast, our first one for 2023, and it's episode 80. We're clicking up there quickly. And let's not forget about our sponsor, the ALTI, the Audio Loudspeaker Technology International, great organization for networking within audio manufacturers. So without delay, let's say hello to Simon in Japan. Good afternoon, Simon.
Afternoon, how you doing?
And good morning, Mr. Marco Simon, CTO and co-founder of AudioScenic, based in Southampton in the UK. How are you doing, Marco? Sorry.
Good morning. I'm doing well, and I'm very happy to be here talking to you today.
Okay, so yeah, we saw AudioScenic with their big press release announcing their technology inside the Razer gaming soundbar product, using optical sensor to target and head track people, and then do some audio DSP technology to create a bubble of audio around people's heads. So maybe we'll start with a presentation to introduce the company and the technology.
So yeah, first of all, you can see now it says company and technology. So I'm going to tell you a bit what is AudioScenic. AudioScenic as a company is founded around 2017, and it was founded by Professor Filippo Fazzi and myself. We were both working together at University of Southampton in this place called the Institute of Sound and Vibration Research, which is a place in the UK, a key center for research in audio in Europe and in the whole world. And in this place, in the ISVR, there was a long tradition on working with CROSSTALK cancellation systems, reproduction of spatial audio or binaural audio with speakers in front of you, okay? And then we kind of built on that. There was this long tradition coming from the 90s. There were like seminal papers, key papers that had advanced this technology. And then Filippo and myself, we were working in a UK research program, which was a big collaboration grant between various universities, University of Salford, University of Surrey, BBC R&D, and Southampton. And what we wanted to do there is that basically the whole aim of the program was to bring spatial sound into people's houses. Okay, 3D audio, spatial sound, immersive sound, however you want to call it, because this is when the program started, 2015. The only reference back then of spatial audio, apart from headphones, is 5.1 systems, multi-channel systems. Mm-hmm. And these are systems that maybe some people can put in some houses, but the normal people, the common people, don't put them because they are not practical, because you need to put loudspeakers all around you, because they are expensive, they don't have space at home. And we said, well, can we give the same experience or even better with just a soundbar? And this is when basically we started working with loudspeaker arrays, and we put head tracking, because the technology of CROSSTALK cancellation already existed for many years. Okay, first patent goes to 1968. However, it had a very, very strong sweet spot, and this is what basically we solved. Okay. Mm-hmm. So if I advance in my presentation, just to tell you a bit about the company, this is AudioScenic right now at the moment. We are all based in Southampton in the United Kingdom, because we are associated with the university where I spin out. We have all our engineering in Southampton, and then we have a business development presence in China, in Shenzhen, and in Taiwan. Okay, that's our company right now. We just closed another funding round, our Series A, just before Christmas. We haven't even done an announcement because we were busy with CS and all that. But we expect that in the next year we will grow to be twice the size and be able to follow more commercial opportunities. This is what makes AudioScenic a particular company and a different company from others trying to do, like, let's say, virtualization effects or post-processing effects for 3D audio with speakers. And is that our technology, there is always a symbiosis, an integration between audio and head tracking, which is done with computer vision or with other methods. And what head tracking does is knowing the position of the ears of the users with respect to the speakers. Okay. And then what we are doing is that we're using sound field control, is the technical name. We are directing how sound is radiated in space, so that this is always the best at the ears of the users. And because of that, what we do is that we can create large difference in pressure between both ears of the users, for example, and create what we call virtual headphones. All right. Mm-hmm. And this is really how, in a nutshell, in a very simplified way, this is what we are doing. For example, with a soundbar, we have two beams, one beam from the left ear, left channel of a binaural signal, another beam for the right ear, right channel of a binaural signal. Okay, and then once we have that, we have virtual headphones. And what happens that if the user moves, then what happens is that we adapt these virtual headphones in space, all right? And then they always have the best spatial signal. And because they have virtual headphones, then we can render any content, okay? Like any spatial audio content. This is like the simplified version for one person. This is a research that we're currently doing into how to adapt this for more than one person, So I have there in my bag a very large array. We use that as reference design to basically develop what we want to do, which is a home cinema solution. Okay, a system that works for one person, for two people, and that then it can turn itself also in like a more normal soundbar with Dolby Atmos or something like that. Okay, or if we want to invite our friends to watch the Champions League or the Super Bowl in America or something like that, So yeah, basically just to repeat again, the good thing is that our technology, because it's in a nutshell headphones, so it's compatible with anything, okay? From stereo to object-based audio to binaural and 3D sound in the middle, because any format that is spatial, you can convert it to binaural, And the combination of good content and also like this way, which is basically the creation of virtual headphones, is headphones that you're not wearing, gives a very good basically sound experience or performance. Okay, and I just want to put this slide here because this is from the Razer Leviathan V2 Pro, which is the first product with our technology that was released at CES. The soundbar got 12 awards of best in show. Okay, and AudioScenic was also awarded by Audio Express like best technology in the show, because it's a new way of listening to spatial audio. It's like basically you're in front of the device and you're hearing sound all around you. And because you're not wearing anything, it's very, very realistic and very immersive, So basically reproduction of binaural audio with speakers, very, 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 it's very plausible and very realistic. And I think because we have been able to tailor that with the user adaptive experience, you're always on the sweet spot. It's very, groundbreaking, and in the end, it works very well.
Okay.
What we do in AudioScenic as a company is that we provide a set of our core IP technology is our 3D audio rendering, okay, that we call it Virtua. And then what we also provide in our software is a set of audio dynamics and equalization. Sometimes if you're making a product, you can have certain effects like backwards, like a DRC, which is on the amplifiers. This can also live in our software, okay? And sometimes the customer can want to have that to really gain speed to market. And we also, it's very important, something that we need is the head tracking software, okay? And in this case, the head tracking can be, we have our own head tracking. We can also work with third-party head trackers.
Okay.
So
would you, those guys like Toby out of Sweden, would you have a relationship with those kind of guys?
We can work with them. Yeah, we haven't openly at the moment engaged with Toby, but we are happy, Yeah.
Okay.
Cool. As long as any head tracking that provides the accuracy that we need and the speed that we need is welcome.
Yeah, they do the retina tracking.
And sorry, I'm going very fast through the slides. If you want to ask me anything at any moment, please.
No, don't worry, we will. We will.
Okay, perfect. So basically, when we combine this software that we have developed, okay, with a speaker array, and speaker array is basically an aggregation of speakers in certain form. This speaker array can be a soundbar, but it can also be embedded on a TV or embedded on a smart speaker or embedded on a laptop. Okay. So basically, once we combine these two things, we have what we call personalized listener adaptive 3D audio. Okay. And we say it's next generation user adaptive spatial audio because it adapts to the user, basically.
Okay.
So, and basically what we do in AudioScenic is that we license our technology to partners. Okay, that's our business model, basically.
Okay.
As a company, And Now I wanted to talk to you a bit about what use cases where you can apply the technology. Okay.
Okay.
So the first one is basically next generation soundbars for immersive gaming. Okay, and this is a render which is a couple of years old, but it's basically it says Corsair. It doesn't have to do anything with Corsair. There is one of the first iterations. So when we developed the actual soundbar that they became later the Razer Leviathan V2 Pro.
Okay.
And the idea that you're in your desktop like I am right now, and I'm listening to sound with that, and I'm playing video games, and I don't need the headphones because I'm listening to my colleagues,
Right.
my colleagues, my enemies or my friends, that we're playing
Yeah, get it.
or whatever. And what we've done is basically we've implemented this soundbar in two ways. One is a standalone soundbar, which has an SoC inside, in this case an NXP IMX8M. And this SoC will do all the head tracking and will also do all the audio DSP. Okay.
Okay.
This is one way where we have implemented the things. We call that the standalone because it's a standalone device. It's like the Leviathan V2 Pro. Basically, you just take the soundbar, it works.
Mm-hmm.
And then other way we have implemented this is with in Windows 10, Windows 11 as well, in which we have offload part of the processing into the computer. Okay, and in the end, it's like two different implementations. One of them can achieve a lower bill of materials.
Okay.
So that's the idea. This is also something where we are working at the moment. Basically, this is our laptop reference design. Okay, and this is how to show how the technology can be applied into laptops. And basically, this is something that we build a mock-up with 3D printed, but we built a small soundbar with actual laptop drivers. Okay.
Okay. Yeah.
To show that the technology could be scaled down, because we think that laptops is also a very good place where the technology could be applied. Because in laptop, you have a camera already there, no? So you don't need to put a camera. You can use the same camera that we're using now for the video conferencing, that to do user tracking, and you can embed speakers.
And does it create enough of a privacy bubble where the sound doesn't spill out too much to the neighbors beside you?
No, because
Okay.
I will tell you another slide later about privacy. So we are also working in products that create privacy.
Okay.
But to create privacy, you need more loudspeakers.
Oh,
Okay.
Okay.
So to do spatial sound, as I'm going to explain later, to do binaural reproduction with loudspeakers, 2 speakers are enough.
Okay.
But if you really want to, and for example, for robust 3D sound reproduction, we recommend to use 5 speakers. Okay.
Okay.
If you really want to do beaming of sound, you need more loudspeakers, and the more the merrier. Okay. So we also built a system that has been forming, or for example, this one, if you go to our YouTube channel, you can see some videos of beamforming with this array. This array has 24 speakers. Okay. It works very well for beamforming, but that's what you need.
Right. Okay.
Beamforming and audio focusing, either or you use traditional speakers and traditional array techniques with lots of loudspeakers, or you use an ultrasonic array, like other technologies that we're providing. We're using ultrasound array, and the ultrasound array is very directional. It doesn't produce low frequency, but it's very directional.
Okay.
But directional audio is something, or like audio is something where size matters. And in directional audio matters a lot. The dimension of the array is what determines, and the number of loudspeakers, but the dimension of the array is what determines if the array is directional or not.
Okay.
Main thing. But yeah, with this, we hope that we'll see laptops coming with and incorporating this technology in the years to come.
Okay. Good.
Very much. This is also a render of something we'd like to see in the market also in 1 or 2 years, which is it's a home cinema soundbar, and is this animation that I showed you before, where a soundbar that can transition between two people, provide spatial audio for two people, and then work as a normal soundbar.
Right. Okay.
So this is basically where we want to use sound focusing, okay? And we think that if we have soundbars that have a large enough number of loudspeakers, let's say 12 or 16, we can use them to create a bubble of sound. And that basically works. We have in our suite at CES, we have a demonstration of this. Why is this important? Because, well, many people are since COVID, we have many people that are working at home and working in the office, you know.
Mm-hmm.
What do we want to promote to do with this? We want to promote, again, a virtual headphone communication. And that's that I am in my office and I'm receiving a call and my colleague is there and my colleague is not disturbed by my call, okay?
Mm-hmm.
Right now, we are doing that with headphones, but headphones can be very tiring at the end of the day. You can see people working on call centers, working on displays. If they could have that communication without headphones, it would be much more natural,
Right.
Apart that, because we are basically creating headphones, we can render 3D sound. And what we can do here is that we have a row of people in a meeting, and when they speak, we can acoustically locate them where they are, And there are some teleconferencing clients that already have applied this technology and adopted this technology, like Dolby.io, for example, has this technology. In Zoom, you can transmit stereo. I don't know if they have already implemented positional audio, but Teams and Zoom, they say that they were going to adopt this technology. So it's also that you can do something that you also can do with our technology and with using virtual headphones and bubbles for spatial audio reproduction. Okay. And for teleconferencing. And the other use case, all right, where we are working and where we have applied our technology, nothing commercially, but something we would like to see in the next year to come, is automotive. And last year we did a project of, in this case, it was a independent listening zones, okay, where basically we were having one person that was listening to music and another person was listening to speech, which in this case was the GPS, okay, was the driver. And apart from that, because we use our technology, and again, we're tracking the position of users inside the car, we have sound which is independent between two people, and that cannot be spatial. Right?
Okay.
So, I mean, these technologies, many people are trying to do the same things in the whole world. We need to take them with a pinch of salt. You are able to do, one person has speech, the other person has music, sound, reproducing two different contents of music with a kind of quality is almost impossible here, unless you have ridiculous arrangements of speakers here and, like that. We are thinking on the car cabin of today is quite hard.
Right.
Very much. And then also to show you something which is our tuning tools. Okay, that is basically something that allows us to control the quality and control the EQ and control the DRC and control the spatial characteristics of our algorithms. Okay, and then the acoustic engineer can basically play with that to give a certain color or a certain tone to the products. Okay, that's something that we provide. Yeah, and this is basically the kind of company presentation and company pitch. I now would like to dive a bit into the theory of how all of this works. For if somebody listens until here and they haven't fallen asleep, now I would send them something that will send them to sleep finally, which is the theory, but it's also very fascinating, really.
This is good, Ben.
About how the technology works. And it's basically all to do about 3D sound and basically reproduce sound. So when we have normally 3D sound, we use a binaural microphones, okay, which you a dummy head or some kind of We can also synthesize it via HRTF. But when we are thinking about 3D sound for headphones, we get two channels. Okay, we will get a left channel. Put my pointer here so that you can see me better. We will get a left channel and we will get a right channel here. Okay, and then if we capture that with a binaural head, what we do is that then we basically feed it straight and reproduce it with headphones, you know. And I think most people probably is familiar with this through Apple Music, or maybe they have listened sometime in their life to the binaural barbershop, which is very is a very good piece of content. So basically they record it with a dummy head, and then you just listen with headphones and you have the feeling of being there. And that's the power of binaural, which is so good and so captivating. So what we want to do is, well, we don't want to use headphones, okay? We want to use virtual headphones. And for that, what we are going to do is that we are going to create and use a DSP system that is going to basically create these virtual headphones here. Okay, it's going to produce a maximum of pressure in one side and a minimum of pressure on the other side, and it's going to give us the virtual right channel, and then a maximum of pressure on the left ear and a minimum of pressure on the right ear, and will give us the virtual left channel. And then anything that we have recorded here, then we're going to reproduce it, and then the user is going to receive here the information as if sources were coming from different positions, and he or she will believe that is there acoustically. And that's really how the technology works, okay? Basically, how can we do that? Okay, so this is the, let me then, laser pointer, no, I want basically, that should work, yeah, I have this here. So how does that work? So let's say, basically I have two speakers in space, and we're going to be talking here with two speakers at the beginning because it's easier to explain. But and then I have my speakers connected to a computer, which is basically a digital signal processor, right? And for these animations, I want to thank to Filippo Fassi, my co-founder, because he created a long time ago for some of his lectures, and he let me use them here.
Okay.
So we have a focus point, and basically what we know here is we know in space the transfer function between these speakers and this focusing point. And we know this transfer function because we have characterized it, because we have measured it, or because we have modeled it, you know, because in space, sound is going to propagate proportional to the speed of sound. So I can know and I can model how long one speaker, the one that is closer, takes to arrive to this focus point, and one speaker, the one that is farther away, how much does it take to arrive to this other point. So when I know these timings, what I can say is like, well, if I want both of them to arrive in time at this point, what I'm going to do is that I'm going to introduce a delay in the speaker that is closer to this focusing point, so that I will delay it, and then both of them arrive here in time. Okay, and then what happened is this one has fired first, and this one has fired after, and then a wave is going to propagate that in this direction is going to create a plane wave if we are very far away, and it's going to arrive with maximum of energy at this point. Okay, and that's a constructive interfere. So my speakers have both blown an impulse, have played an impulse that is arriving in time. So with that, we have what we call a constructive interference. Okay, it's what we have here. So that's great. We can basically then say, okay, this focusing point is my ear. I want a maximum of pressure in the ear. But then what is happening if I want to do sound cancellation? I want to create a destructive interference. What I'm going to do is that I know where I want my cancellation point to be. So what I will do is that, well, if I basically change the phase of one of them, they are going to arrive with cancellation at this point. Okay, and what happens? This guy outputs first because he's farther away. This guy also outputs, but with negative phase. And you can see that in this angular position, the energy is very much reduced. In theory, their energy is zero. Okay, in basically practice, is something like that. If you go to the web page where the Razer Leviathan V2 Pro is It's a feature. There is an explainer that explains the beamforming technology, and they have done a great video also explaining the constructive and destructive interference
Okay.
problem. If
We'll
they
put
show it in
those.
1D, in this case it's 2D. In real life, it happens in 3D. But it's
Okay.
like that.
Yeah, we
Yes.
can put the links to those in the description so people can check it out later.
I think that'll be very cool. So yeah, basically this is what happens in a nutshell, okay, of how the technology, what is the physical phenomena. How do we implement 3D audio with speakers? Okay, so basically, what happens is that well, let's say I have this source here, this that I want to reproduce, which is a source that basically is here at my right, and that if I record its input response, or if I record a certain length of audio at both my ears, is going to produce different content on my right channel and on my left channel, my left ear, that will basically, in these differences that arrive to the two ears, will be embedded the binaural signal that will tell my brain that something is coming from there. So, as we said, normally people will listen to this with headphones, but what happens if we want to listen to it with speakers? Okay, sorry. And what we're going to do in order to reproduce this with speakers is that we're going to use a network of digital filters, okay? And it says here digital filters for inversion of loudspeaker response. Because why we call this inversion? Because we want to invert the speaker response. We want to get rid of it. And that's basically how our technology works. You have a soundbar in front of you, but you don't want to hear to the soundbar. You want that soundbar to disappear because the only thing that you want is the binaural cues that are arriving to your ear, all right? And again, we're here basically talking with two loudspeakers because, I mean, stereo is such a common setup, and people have tried to use that and to work with this for many, many years. The first patent of this kind of technology is from 1968, okay, from Attal and Schroeder. But basically, they reproduced the first system. So, I mean, one thing I could do, for example, is just try my stereo speakers and play the binaural recording that I have, and play my right channel to the right speaker, and play my left channel through the left speaker, all right? And I can do that, and the right channel will be reproduced by the right speaker. What happens, however, that I'm also going to hear on my right ear the left channel, and that's going to mesh. It's going to interfere with my binaural perception, because if I really want to hear binaural well, I need to hear only what this guy listen on each ear, okay?
Right.
And this is crosstalk, and that's why this technique, in academic terms, in scientific terms, called crosstalk cancellation, So the Razer soundbar, it says that this 3D audio beamforming, and it's true, it's beamforming because when you have more than two speakers, you start to create beams, which are kind of pronounced, but on the back of that, what happens is that you're doing crosstalk cancellation as well. You're trying to separate what one channel is playing on the other, okay? And basically, we are going to achieve this by using a filter, okay, that is going to cancel whatever signal of one channel is arriving on the other channel, okay? So
is this kind of like with the Beatles? A lot of people love to listen to the Beatles on headphones because George Martin had recorded the left and right separately. So a lot of people are always obsessed with listening to the Beatles on headphones rather than in a stereo speaker environment.
Yeah, really, maybe, I think so. If you listen to that, for example, that you're saying, that a very hard panned stereo track, which is maybe like in the 70s, 60s, like pans were like that. If you hear it with a crosstalk cancellation system, like with a Razer soundbar, you will hear that things sound very, very spatial to you.
Wow. Okay.
They sound here and they sound here. If you listen back with a normal stereo setup, things don't sound here. Things sound like in the speaker and on the other speaker.
Okay.
But for binaural audio reproduction, you really need to separate what arrives to one ear and to the other ear, and that's why basically you can do a test. You can listen basically with the barbershop, with
Mhm.
headphones,
Mm-hmm.
and you can basically then listen to it with stereo speaker, and you will see that with headphones, you are immersed in the barbershop with the stereo speakers. It's with the stereo speakers, And I encourage everybody to basically buy the Razer soundbar because it's the first system in the world that lets you have this. I mean, it's not the first system in the world, but I would say the first system in the world that works in a robust manner and that you just turn it on and works, and that is practical. And you will be able to listen to any binaural content, to play any video game, or also to listen to music in a way which is it's very special, because you just put it and you are hearing stereo to one side and to the other.
Okay.
And then just basically digging a bit into the theory here. So we need to use 4 filters, okay? And that's very important. And it's because this is my 4 filters for inversion. And that's because if I have one speaker only here and I want to equalize my whatever I listen in a given ear, one filter is okay, is enough, However, now we are asking 2 things to the system with 2 speakers. We're asking to have an equalized signal in one ear and then cancel whatever I'm listening in the other ear, okay? And in this case, this is a system of 2 equations that needs 2 variables to be solved, okay? In one equation is one of my ears, the other equation is the other of my ears. In one, I'm asking to have maximum pressure. In one, I'm asking to have minimum pressure. And that's why per channel, I need to have 2 filters, okay? I need to have one that reproduces, well, both of them work at the same time. They make sure that I have maximum pressure in one ear and minimum pressure in the other ear, okay? So with these 2 signals, with these 2 filters, I make sure that my right channel arrives to my right ear, and I make sure that my right channel doesn't arrive to my left ear. Okay. All right. And then I do the same with the left channel. I make sure with other 2 filters on the left, that are basically connected to the left input, my left input signal arrives to my left ear, and then I make sure that my left input signal does not arrive to my right ear. Okay. This is very cool. In theory, you say, yeah, it has to work. No, it has to work. In practice, it's a super complicated system, okay? And basically, you say that this is their infinite combination of 2 filters to get left ear signal right, okay? And why is so complicated? Well, so let's take a look at how these filters that I need to do and what the speaker signals look in time, all right? And this is, again, I need to thank for these slides to somebody that was in ISVR, Takashi Takeuchi, that basically also had another company that was working with 3D sound, and he created these slides, I think, time ago, and I think they explain the concept very well. So let's say that this is my target binaural signal, okay? This is what I want to listen on my left ear, and it's an impulse. And I only want it to arrive to my left ear. So, well, let's see how we can make it. So what we can do is that my left speaker plays this impulse because it's the speaker that is closer to my left ear in front of me, okay? It's going to reproduce it. And very good, that impulse will arrive to my left ear, okay? This is what I wanted. Amazing, perfect, I have my impulse. However, because sound propagates in the space everywhere and because we cannot stop it, unfortunately, this impulse that has arrived to my left ear arrives a bit later to my right ear. No, this is not what we wanted. In our target binaural signal, we only wanted this impulse here, not there, because otherwise it's going to mess with our perception of the spatial sound. So the algorithm, because it's very clever and because it knows that in the right ear this impulse is going to be received, says, no, don't worry, because before it arrives, I'm going to emit from the right speaker another impulse in opposite phase that will arrive and will cancel this one. Very good. We have canceled the impulse in the right ear. What happens? What happens is that this impulse that we have made to cancel this impulse at the right ear is then going to arrive to the left ear. And that's not what we wanted, because we just wanted one impulse. We didn't want that. This is a different content than the one that we wanted initially. And then the algorithm says again, no, don't worry, wait for me. I'm going to now make another impulse in opposite phase that will cancel this one on the left ear. And you can see there. But unfortunately, this impulse is going to continue propagating and it's going to arrive to the right ear. And then the algorithm that is clever is going to emit another impulse in opposite phase. And you see, for just reproducing this first impulse that we wanted in the speaker, all this other time information is required, you know?
Mm-hmm.
And that's why these systems become so difficult to basically control, you know, and implement, because they require a signal processing system, which is kind of a very stable sometimes, and that needs to output lots of cancellation energy. This is all energy in the end that is output, and that puts some constraints in the dynamic range of the speakers, you know, and all of that. This is how it looks in time. So just to play this impulse, we need to put all this garbage after, okay? And that's why they become so complicated. If we look at how this basically, how this looks in the frequency domain, it looks something like that. And what happens is that this is the norm of the crosstalk cancellation filters, and at some frequencies needs much more energy than at others, you know. And this is what we call ill conditioning. And this is a very common problem of crosstalk cancellation systems, and in the end of any kind of array processing, line array processing, there is always like constraints in the dynamic range that you can output, you know. And I'm going to talk about a bit more later about that. So how does this look in the time domain? Okay, it looks that basically in a simulation, just to play one impulse, look how much we need to play. This guy is going to receive an impulse on the right ear. Okay, see, this first impulse is going to arrive, and he listens it. But look how many others we need to put so that nothing arrives after the first impulse. You know, and that's really very, it's very fascinating and that's the really technical problem of crosstalk cancellation. You know, very much. Yeah, and I have some more slides that I can talk to you about more other kind of technical
questions. Then, when you're developing a system like this, there must be a fairly lengthy process of characterizing the acoustic system.
Yeah. Basically, so there are lots of really you know, like so I've been working on this a lot, and people before me have been working a lot, and that's so many measurements. You know, we have even basically this thing that you see there is a robot for automatic measurement of system. You know, it has two microphones, and basically we can move the microphone around, and we can say where people are, or how the sound really is. You know, because in the end there are so many things that affect this sound. This is not only the system, also the room. You know, and that's why the head tracking becomes so important here. You know, and I can go basically a bit forward in some basically slides that I have here. This is how small the sweet spot is, okay, for those systems. And this is basically a simulation, again, just using two loudspeakers for simplicity. And it's the headphone effect. And this is kind of how the headphone effect looks with angular deviation. We can get this is dB. I forgot to put the label here, but this is dB of cancellation. When you are very much on where your filters are doing this cancellation, you obtain a lot of pressure difference, okay? But if you move away even a little bit, okay, where we calculated that was 3 degrees, which is 1.5 centimeters. 1.5 centimeters still is kind of okay. But in the moment you move 3 centimeters, which is just very small position, you see there are some areas where this cancellation that before was kind of large is now like really being really reduced.
Okay. So the filter characteristics fixed at design time?
So what our technology does is that it calculates maybe 30 times filters per second, and it changes the filters.
Okay, but it must be a layer where you've characterized, say, the acoustic system or calculate against.
So our technology is based on models of physical models of propagation, and that's what we use for characterization.
Okay.
And that's why we can very fast estimate the position of users. Because people and other for Audoscenic competitors are trying to do this like with measurements or transfer functions. That's very hard because you need to do lots of measurements.
Yep. And in terms of frequency range or bandwidth of how well it works, I mean, you can't really have a huge array of very large speakers for low frequency sound, so you kind of taper it from some into mid and high frequency, and then low frequency is kind of a uniform field.
Yeah, so I think basically our technology at the moment works as so what we are doing is that we provide a low pass filter and then a high pass filter. And the low pass filter are for bass, that basically the bass is not directional, but then everything above the high pass filter, okay, will be controlled by the algorithm. Basically, what I was going to say, the technology can be applied for any number of speakers, okay, and arrays of any sizes. You can see here, from a laptop to a soundbar to basically very large arrays that we have been using here for development, okay?
Yeah.
And basically, in this case, for example, on this large one that we have here on the left-hand side, I think the cutoff frequency for where the algorithm was starting to work were 100 hertz.
100 hertz is still very low, actually.
Very low, yeah.
Lower than I would have expected. And then, and each channel needs 2 filters, so it escalates quite rapidly.
Yeah. So from a signal processing point of view, this thing needs lots of signal processing. Yeah. Say, I mean, in the Razer soundbar, it has 5 speakers. Each speaker has an independent channel and basically has a filter, so a network of filters. Yeah.
Yep.
Very much.
Okay, very interesting. And so we've talked about that aspect of it, and the head tracking is something, a kind of critical element. If you've got something more you could tell us a little bit about that, because that would be another, it depends on the hardware that you have and things like that too, I guess.
Yeah, so I think basically this slide where you see this red line here, that's let's say it's kind of the minimum that you should get to start having a good specialization, okay, a good immersive minimum crosstalk cancellation. If you don't do head tracking, and you move even 3 centimeters, there are some frequencies where you're not getting this,
Okay, I got it. So the higher, the better. In sort of
higher, the better, yeah. And really, you would like this to go even higher. This is what happens when you use 2 speakers. You would like this to go even higher,
Yeah.
And that's why we recommend also to basically use more than 2 speakers. I want to show you what happens here. This is the crosstalk cancellation, the headphone effect. The higher, the better.
Yeah.
Okay. So in this basically left-hand side, we have the CTC, the headphone effect. And in this right-hand side, we have the AE, which is the array effort. And basically it's a measure of the electrical power that the system needs to obtain this headphone effect.
Yeah.
So this one on the left, we want it to be as large as possible. This one on the right, we want it to be as low as possible, because if we need more norm, it means that we are basically compromising the dynamic range of our speaker. So if we just have 2 speakers here, this is basically has been what the whole of the audio industry has been trying to do for many years, just use 2 speakers to do crosstalk cancellation. Yeah. What happens is that there are certain frequencies where you are not obtaining cancellation, okay? Because it has to do with the spatial aliasing, and there is a given frequency where you cannot have a maximum and cancellation.
Yeah, wavelength related, essentially. Yeah.
Basically, that happens, and this is the effect that you see here.
Yeah.
But if you add a 3rd speaker, okay, you basically increase the spatial aliasing frequency, and you only have a minimum at a much higher frequency.
Yeah.
So you obtain the range. And that's why we say to people who want to implement our technology, use 3 speakers a minimum, but use more than 3 speakers, because if you use 4, you increase, okay, your range. And if you use 5, you even increase it a lot. Yeah. And in this simulation, it's telling us that we can arrive up to 20 kilohertz.
Yeah,
Okay,
I see.
in practice, this is a simulation, okay? In practice, you don't arrive up to 20 kilohertz. However, you make it much more robust, maybe arrive to 10 or something like that. And that's why you also reduce the dynamic range that you need at higher frequencies, And that's why this is very important. So the more the speakers we use, the more robust we make the system, also to inaccuracies on the camera system, because the camera system we trust it, but sometimes it's not accurate,
Yeah, sure.
But it's and this is basically just to show you how the simulations that we were putting before, how they will work with an array. With an array, you have many more speakers, so whatever you're doing becomes much more robust.
Yes.
Also, once you have an array, this is what happens, okay? So this is the comparison. The blue radiation pattern is the radiation pattern that a crosstalk cancellation system obtains when it tries to create virtual headphones, okay? And you can see it's going to make a beam, which is very, very strong in one ear, and a notch
in
the other ear, okay? And in theory, you see, this is how something will look on the free field. At a given frequency, in theory, the array having 2 speakers, or I think in this red radiation pattern has 16 speakers, they should work the same to create this virtual headphones effect, However, we don't listen to sound in anechoic chambers, okay? We listen to things in rooms that have reflections and that are affecting. So by using many more speakers, we create a narrower beam. And this is what is the beamforming effect. And this is why when we have more speakers, we focus sound and we create a bubble of sound, And that's why the Razer SOUNDBAR, it says it has 3D audio beamforming, because it's a combination between crosstalk cancellation and beamforming, basically, very much. And just Simon, to show you, basically, this is what happens in real time. We have these beams, okay, and this basically, we have a beam for the left ear and a beam from the right ear. These are the ears of a user here, these 2 dots. If the user moves, the position of these beams are changing in real time.
Right.
Okay, because we are changing in real time the filters that are creating those beams in the speaker array, which is for this thing here. Yeah, very much.
Fascinating.
Yeah.
Okay.
And yeah, man, I think this is the end of my presentation. Yeah.
All right.
I think, this is basically we are Audoscenic, and that's our vision. We want to be the enabling technology behind personalized and immersive audio reproduction, offering a revolutionary listening experience in a multitude of everyday situations without the need of headphones,
Yeah, I mean, at CES, I got the chance to hear the demo with the Tectonic Audio Labs drivers, and I mean, I could say that I don't want to do it right here because I'll go off mic, but basically, it really does kind of track your head and follow you around, and left and turning right. It captures all that kind of experience. It's quite impressive.
Yeah, so the Tectonic demonstration, we use the Tectonic technology because like this Tectonic VMR drivers are a bit more point source like. It improves at higher frequencies how our technology works, because basically they work a bit better, Yes. And that was a good demo, and and you can really feel it. So I don't know if Simon, you had the opportunity to listen to our technology, but
one day.
Yeah, it sounds like I can tell you, but once you listen to the system, you say, "Wow,"
Yeah. I'm looking forward to it.
Yeah.
All right.
Yeah.
Okay, so I guess if people want to get in touch for technology, they can. I'll put your contact information for the right person or yourself below.
You can contact me. You can contact anybody at AudioScenic. That's good. Yeah.
Okay. All right, Simon, did you have any follow-up final questions?
I'm good. I'm good.
All right. Okay. Well, we encourage everybody, put your comments down below, questions and anything else that you're intrigued by. Please give us a like, subscribe, and share, and all that good YouTube and now Spotify and all the other platforms. So, Marcos, thanks for joining us today. We appreciate your time.
Yeah, I thank both of you for hosting me, and it's a pleasure, and I look forward to seeing the video. Yeah, and thank you very much. Yes.
Cool. All right.
Yeah.
All right. Okay. Thanks, everybody. We'll see you next time.
Bye-bye.